So I'm a postdoc in this Cambridge analysis group at the University of Cambridge. And it is the group of Carola-Schönlieb, who should be here, but he couldn't travel because of some reasons. And so I will give the talk. And so since I started my postdoc in January this year, so I've been working on this cryo-EM project. So I'm quite new in the field, but I'm going to present some results or some approach that we are trying to use to address this problem of recovering the atomic structure of a macromolecule, such as a protein. And so there is different kinds of information that we can use, like we can use biological knowledge, like we know that, for instance, a protein is a sequence of amino acid residues, and they form a kind of a chain. But from this information is very hard to recover the structure. There are new techniques based on deep learning, like AlphaFold or AlphaFold 2, and so on. And the other kind of information that we can use is these cryo-EM images, which are very noisy, but we have a lot of images. The problem is that they are very noisy. And the problem is also that the orientation of the particle in each image is unknown. So these are all difficulties. And typically from the cryo-EM dataset, you don't get directly the atomic structure, but you get something like the 3D density. And then if the resolution is sufficiently high, then you can go from this to this, also combining different techniques. And then the other difficulty in cryo-EM is that we are not only interested in recovering one conformation of the molecule, but we want to recover all the possible conformations, because this is important on the biological function of the protein, for example. And the good thing in cryo-EM is that we have in every image there is a different conformation, so we can use this data set to recover this heterogeneous structure. So at the end, what we want is to determine the set of possible conformations, like the structure of the set, and then we want to construct a map which associates to every point in the conformation space the corresponding structure, like this thing. So there are two kinds of heterogeneity. There's the discrete heterogeneity, when the structures that you have in the data set belong to a finite set, and then you want to determine the structure corresponding to every class. And there is also the case of continuous heterogeneity. That is the one that I'm going to address today. And then in this case, the set of conformations is some manifold, compact manifold, and embedded in some higher dimensional space. And then you want to construct the map from this manifold to the corresponding structure. Okay, and this is how the images are modeled in cryo-EM. I think it is not worth it to talk about this again, because it's the last day in the conference, and we have been talking about this a lot. But so we have this would represent the 3D density of the particle. Then we apply some rigid transformation, which is a rotation plus a translation of the density. And then we apply this projection, which is a integration over the z axis, and then we convolve with the point spread function, and we add noise. And so from this volumetric density, we get this noisy projection. Okay, so there are several methods to address this continuous heterogeneous cryo-EM reconstruction. So the most recent ones are based on deep learning and use this variational autoencoder idea, like in CryoDragon, where the images are projected in this latent space, that encodes the conformation of the particle in the image, and then using this latent representation with the image pose, there is a decoder which is trained to determine the density of the particle. Then there is a similar idea developed also very recently by DeepMind, which uses also a variational autoencoder to project the cryo-EM images to a latent space, and then from this latent space to recover the atomic structure. And then from this we can just simulate the image and compare with the data. But the moral here is that we have a low dimension representation of the particle in the image, and then we use the pose to reconstruct the atomic structure. We have to mention also this other approach, which is based in the same idea, but it's based on PCA, and it has been used by people here in the room. And it consists on estimating the mean volume, then estimating the covariance matrix. So this is a voxel representation of the density, and then the covariance matrix is this huge matrix, and then you estimate it using the cryo-EM data with the pose of the particles. And then the reconstruction is obtained as a linear combination of the principal eigenvectors of this covariance matrix. The problem here is that this matrix is very big, so it is very expensive to compute this, but if you look at the posters, there is one by Mark, which doesn't need to compute all the covariance matrix, so only with a few rows you can carry out this reconstruction, and it allows you to consider a higher resolution. You can consider more voxels in your reconstruction. But at the end, also here, what you obtain is this PCA coordinates of the particles, which somehow encode the information about the conformation of the particle in the specific image. So what do we want to do? So what we want to do is to use the information that can be obtained by these other methods to estimate the continuous heterogeneity of a flexible particle or a flexible molecule. And we want to use this low dimension representation of the conformation that can be obtained by these PCA components, that would be these betas here. Or we can use the representation in latent space from the variational autoencoders. So this is something that we want to use. Then we want to use also the pose of the particles that can be estimated by using other methods. And then we are going to use also an atomic structure of one of the conformations. So our goal is, given an atomic structure, we want to determine, using the cryo-EM dataset, how this given atomic structure is deformed in each of the cryo-EM images. And as we will see, we are also interested in using other structural properties about the macromolecule, like secondary structure or some parts of the molecule which are more rigid, and then you know that they are invariant under the different conformations. Okay, so let's formulate the problem. So we are going to use the prior knowledge about the structure of the protein or the macromolecule. So in our case, we are going to make this structural assumption, which basically says that the molecule of interest can be modeled as a discrete curve, because it can be modeled as a chain. This is the case, for instance, of a protein in which, in the protein you have many atoms, but if you consider the backbone of the protein, it forms a chain. So In this case, our atomic representation does not represent all the atoms in the macromolecule or in the protein, but it would represent the position of the C alpha atoms that determine the shape of this protein. Of course, we can extend also our method to more complex structures, but we are going to stay with this discrete curve structure, just because this is the first like kind of experiment that we want to consider. Okay, so for a given atomic structure like this discrete curve, we can associate the corresponding 3D density that we are going to model as a Gaussian model by adding by adding Gaussians centered at every atom position. Then from a point cloud representing the atom positions, we obtain this 3D density. So the problem is to use the cryo-EM dataset to estimate these 3D structures. So we want to minimize this loss error. So this is this volumetric representation, and then we apply the forward operator in cryo-EM, which is the projection and the CTF and everything, and we compare with the images, and we optimize over point clouds satisfying this. But of course, this problem is not that good. Yeah.
What actually is the term they're representing? Because if you fix an atom or a structure, then you don't need a coefficient gamma j, gamma I.
Gamma I.
What is gamma I?
Gamma I is like the weight of the density, like how much mass you associate to every.
But if you fix the atom, this atom has already this density inside.
Yeah, but one thing is the position of the atom, and then there is the density that you associate to this atom.
So you don't have the information what this atom is.
Yeah. So gamma I is different for every.
So you don't go to this is this specific. This is carbon. Say this.
Yeah. So this.
Don't say that. You just replace it with the density.
So every amino acid, let's say, amino acid residue has an associated density, which depends on the number of atoms, and you approximate this density by a Gaussian, which has some width and some weight. So this is known. This is known by the chemical composition of the protein. Okay, but so we have this problem. And this, of course, it doesn't make sense because we have too many parameters to estimate. We have 3mn, and n is the number of images. And of course, if we consider that problem, we are going to have a lot of overfitting because the images are too noisy. And we are not actually using the relation between the different structures. And also we are optimizing over this set of, with this constraint that, let's see what we can do. So first of all, what is the relation between the different structures? So we know that if we are given a conformation or a structure of the molecule, how all the other structures are obtained. So they are obtained by applying a deformation of the structure, which accounts for the different conformation. So we have a curve, and we are going to deform it some way. And there we are going to apply a rigid transformation, which represents the pose of the particle. So this is how all our structures are related. And here since we are going to assume that we have estimated the pose of the particles, we are going to assume that we know this rigid transformation, but we don't know the deformation. And what we are interested in here is in recovering the deformation of this kind of discrete curve. Okay, so how are we going to do it? So first, under the under this assumption 1, which says that my point cloud is a discrete curve, I can write this discrete curve by using this representation where I have one position of one atom, and then I have the vectors connecting every 2 consecutive atoms. And then my discrete curve can be represented by this reference atom position and then all the other unitary vectors, which are then scaled according to the distance between every 2 consecutive atoms. Okay, and using this representation of the discrete curve, I realized that a translation of the structure accounts for translation of this reference atom. So translation, it leaves invariant these other coordinates in this representation. Okay, so this is one part of the rigid transformation, but we also have rotations, and then we also have deformations, which are not rigid. So this representation is not enough for us because we also have other transformations. So the idea here is to use this idea taken from the representation of smooth curves in R3, which is to use these Frenet-Serret formulas. So the idea is very simple. It says that any smooth curve in R3 can be represented using a ODE of this form, where T is the tangent the tangent vector of the curve at every point, and then F of S is the so-called Frenet frame, which represents the orientation of the curve in this at every point of the curve. And then this Frenet frame, it solves this ODE, and it gives you a trajectory in SO3 because it's like an orthonormal basis which is varying. And here R of S is a matrix of this form, which is an element of the tangent space of SO3, and it can be parametrized by the curvature and the torsion, which are continuous functions from 0L to L is the length of the curve to R2. And then if you have this and you have like the one position and the orientation of the curve at one point, then you can reconstruct the curve. So what we have here is a representation of any smooth curve as we have a representation of this, any smooth curve, by this position and orientation at one point, and then the curvature and the torsion of the curve. So now if we look at transformations of this curve, we know that rigid transformations can be obtained by changing this initial condition, like the position of the reference point and the orientation of the curve at this point. And then any deformation of the curve can be obtained by modifying the other 2 parameters, which are the curvature and the torsion. So in our case, this represents the pose of the structure, in this case, the pose of the smooth curve, and this represents the shape of the curve, like how this curve is folded. Okay, so this is for smooth curves, continuous curves. In our case, we are in a discrete setting, but we are going to use a similar idea. So it's called the discrete Frenet-Serret frames, and the idea is exactly the same, but instead of a ODE, we have a discrete dynamical system. We have this difference equation for the position of, for the positions of the points in the discrete curve, and then we have this equation for the different Frenet frames at every point, and these Frenet frames are obtained by this. So this is like the T, capital T, is the vector joining every two consecutive points, and then we can compute the binormal vector and the normal vector, like this. And with this, we construct the sequence of Fresnel frames, and then we can recover the rotation matrix that allows us to go from one frame to the following. Okay, so using this representation, we see that any discrete curve satisfying any point cloud satisfying this discrete curve condition can be represented using this dynamical system, where the parameters are the initial condition, like z hat and f hat, we determine the position and the orientation of the curve at one specific point, and then the rotation, these rotation matrices, this sequence of rotation matrices, saying how these Fresnel frames are varying from one point to the following. And now we are gonna, so we have this representation of the discrete curves using somehow the pose and the shape of the curve, and we are gonna parameterize the sequence of the sequence of rotations by using the Euler angles. And now at the end we are gonna optimize over these Euler angles. I know that optimizing over SO3 using the Euler angles is in general not the best idea, because you end up with an unconvex problem, with an unconvex optimization problem, and it's very likely that you end up in a very bad local minimum. But in this case, it can be useful in many situations, because as I told at the beginning, we have a given conformation of the structure, and we are we are looking for a deformation of this structure. So if we have a good initialization of the optimization algorithm, then we can expect that using these Euler angles, we can actually converge to a good minimum. And then so this is the parameter space of our atomic structure. So this represents the position, like the spatial location of the protein, or the particle. This represents the orientation, which is f hat, and then this sequence of angles determine the conformation. Okay, so now if we look at this deformation of our structure from one particle to another, we have a rigid transformation, which accounts for a modification of these two parameters here, and then a deformation, which accounts for the modification of these parameters. So assuming that we know the pose of the particles, we can assume that we can obtain this information for every particle, and we want to recover this, which varies from particle to particle, depending on the different conformation. So at the end, the goal is to construct a map from the manifold of conformations to the sequences of Euler angles. And this is the approach that we are going to use. So here it's very important that we use this sequence of Euler angles which are obtained from the reference or from the given conformation, which is an atomic model. We can compute the Euler angles, and then we want to determine the perturbation of these Euler angles for every deformed structure in the data set. And we are gonna estimate these functions, theta and psi, as a linear combination of the eigenfunctions of the Laplace-Beltrami operator defined on the manifold. And this idea is like a generalization of expanding these functions in Fourier series, just that instead of a Euclidean space here, we have some manifold that we don't know, but we know that if it's a compact manifold, then the eigenfunctions of the Laplace-Beltrami operator form an orthonormal basis of L2, which is the space of functions defined on M. And then we can approximate our functions theta and psi using the first eigenfunctions, which represent the lower frequency. So we are interested not in recovering the vibrations of the structure, but the movement of the parts of the macromolecule. Okay, so now the good thing about this is that here we can use even more information about the molecular structure. Like, for instance, if we have some parts of the molecule that are rigid and they are invariant from one conformation to another, we know that these Euler angles are not going to be modified. They will be preserved. So in this case, we can set the corresponding parameters to 0, and then we know that these rigid parts of the molecule will be preserved. And this can help us to reduce the number of parameters to be estimated and to obtain better results. Now, here, so with this approach, so we need to basically estimate two elements. One is the eigenfunctions of the Laplace-Beltrami operator on M, and we need to estimate the coefficients in this spectral decomposition. So for the first, the problem is that we don't know the manifold, but we can use a known technique in manifold learning, which is also used in the context of cryo-EM by Amit Moscovitch and Amit Singer and other co-authors. And okay, the idea is that if you have a low dimension representation of the conformation in each particle, you can construct a weighted graph, which tells you basically like how similar the conformation in every two particles is. And with this weighted graph, you can construct the similarity matrix, the graph Laplacian associated to this weighted graph. This is the normalized graph Laplacian, and under certain conditions, we have this convergence of the eigenvectors of the graph Laplacian to the eigenfunctions of the Laplace-Beltrami operator, or to maybe not the Laplace-Beltrami operator, but to another linear differential operator for which the eigenfunctions form a basis of L2. But okay, so if we can compute these principal eigenvectors of this graph Laplacian, then in the above expression we can replace the eigenfunctions of the Laplace-Beltrami operator by these eigenfunctions, eigenvectors of this graph Laplacian. And here again we have this theta 0 and psi 0, which are the Euler angles for the given conformation, and then we want to determine the coefficients AK and BK. So we can, using a matrix expression, which is more compact, we can write it down like this. And here, so we want to estimate the matrix A and B, and A is a matrix with this dimension, m minus 2 times k. So m is the number of atoms in our discrete curve, or in our molecule, and k is the number of eigenvectors that we are going to use, and the same for B. And these are the eigenvectors which are computed as the principal eigenvectors of the graph Laplacian. Okay, so we have this now, or we have an approximation to these eigenfunctions. Now we need to estimate the coefficients A and B. And for this, we are going to formulate a minimization problem in which we compare the atomic models predicted for each particle with the cryo-EM images. And we recall that the atomic model can be represented by using these parameters, where z hat and f hat are known, and we need to estimate theta and psi, which we are going to write like this. And we want to estimate these two matrices. So in total, we have 2 times m minus 2 times k parameters. So the number of atoms in the structure times the number of eigenvectors in the spectral decomposition.
Can I ask a question?
Yep.
So I just want to make sure I understand Z hat and F hat. Those are per residue, sort of interior frames that you know, from one point to another there could be some translation, and then you orient where you continue on defining the frame of the next.
Z hat and F hat?
Yeah.
No, this is for per particle.
Okay, they're global.
Yeah. So the global particle is written as a discrete dynamical system like this. So it's a discrete curve, and you can write it down using the position of one of the atoms and the orientation of the curve in this specific atom. And from this, you use these rotation matrices to construct the rest of the curve.
So the curve is between residues for one.
Yeah. So it's between C alpha positions.
Okay.
Yeah.
So RJ would be that frame of each atom.
Yeah, the transition matrix. It's not the frame, it's the transition.
Okay.
Yeah.
And the delta you assume to be constant, right?
Yeah.
There's no stretch between.
No, I assume it to be constant. I know that it can vary, but it's more or less constant, right? The distance between C alpha positions, it's usually more or less constant. It's of the order of 4 angstroms or something
To me,
like that.
this looks pretty much like a model from robotics. Like if you have a robotic arm,
Yeah.
basically it has a couple
Yes,
of
yeah.
points, right? And they do inverse
Yeah, so this is,
It's pretty similar, right?
yeah, it's similar, yeah.
You have constraints on the motion, like in robotics, where you say like only one angle can move or something like that?
Here I don't put any constraint, because in principle, you don't know how these deformations can be. Like you can put constraints. I mean, if you have the more information you have, the more information you can use, and then the less parameters you have to estimate. Also, if you know that some parts of the structure are rigid, like if you have an alpha helix, then all the rotations within this helix will be constant over all the conformations. So you don't need to estimate these rotations because they are all given by that initial atomic model. So in this, sorry. So here, so AK are vectors of length, the number of atoms. So for the atoms, for instance, in an helix, that we know that it's going to be constant, you just take these parameters equal to 0, and then you have only so this part, in all the conformations, it will be moved rigidly. So this is also information that you can use to decrease the number of parameters, and of course you end up with more constrained structures that you are exploring. So you have less flexibility, but I mean, the more information you have, the better. Okay, so once we have this parametrization of the atomic structure using the pose and these Euler angles, which we have constructed as these functions, then we can define this map, which for given these parameters gives us the corresponding point cloud with this initial condition and these Euler angles. And from this point cloud, we can compute we can estimate the volume density associated to the particle. And then from the volume density associated to the particle, we can estimate the cryo-EM image by applying the forward operator. And this is what we are going to compare with the cryo-EM data. So we have, at the end, we have this minimization problem where we minimize over matrices A and B, and we minimize the mean square error of the images predicted by our model with the cryo-EM data. Yeah, and then, of course, this is a non-convex optimization problem, but as we said, we are looking for deformations of the atomic structure. So if we have a good initialization, like if we take, so as initialization, I'm going to take always A and B equal to 0. So the prediction for all the particles at the initialization is going to be the given structure. Is like the given atomic model. And then you apply this stochastic gradient descent, and then you are going to modify these Euler angles for each particle according to the data set. And you only have to optimize over these parameters, which is less than, I mean, it's relatively small matrices. So we implement stochastic gradient descent with initialization A and B equal to 0, because we want, as the initial guess, all the particles to be the same conformation, and then we want to deform it.
I have a question.
Yeah.
So here you're assuming that you're finding the optimal A and B for each particle.
No.
So you assume that all particles come from the same conformation?
No.
Oh, okay, so yes.
No, sorry. Yeah, because every particle has a different eigenvector. So this phi I is different for every particle. This phi I are the vectors that have been constructed from this graph Laplacian. So these are the eigenvectors. These are the rows of the eigenvectors of the graph Laplacian. So, okay, let's go back. So, yeah, here. So we have this graph Laplacian, which is an approximation of the continuous Laplace-Beltrami operator in M, which is the manifold of conformations. And then we compute the eigenvectors, the principal eigenvectors, the eigenvectors associated to the smaller eigenvalues. And then this gives us, for each particle, yes? So
this assumes you have a discretized version of the manifold available of the conformation.
Yeah. So here is where we use this low dimension representation of the particles, of the conformation in the particles, that you can take from this PCA representation or from a variational, from the latent space in a variational autoencoder. You have a low dimension representation of the particles, then you can compute the distances between them.
So when you're doing your minimization and the final, so you already assume you know your phi.
Yeah, you know phi. Yeah.
You know your phi for each particle, so you know where it belongs in this manifold.
Yeah, we know where it is in the latent space, let's say. So you want to construct, roughly speaking, a map from the latent space to the structure.
Thank you.
Yeah.
Are you explicitly computing the graph Laplacian? Isn't it humongous?
Yeah. So
if you have 1 million particles, you'd be talking about a terabyte of.
Mm-hmm.
Yeah, but there are techniques to approximate the smaller eigenvectors, like randomized SVD and this kind of
so you're not using. So you're using methods where you don't have to actually explicitly compute.
Yeah, you want to compute an approximation of these main eigenvectors.
Okay.
But if you could, it would be better. But then, of course, we are using it also depends on the structure of the similarity matrix. If it's sparse, then So you can, for instance, as similarity matrix, you can take the nearest neighbors, and so I mean, there are ways to do it more efficiently. But this is the idea, to compute the. No, in the numerical experiment that I'm gonna show, I used synthetic data. It's very toy models. I just wanted to. I mean, this is still a work. It's the first steps. Yeah. So I'm using a small data set, and you can compute everything pretty fast. Yeah, but the idea is this: that you can approximate these eigenvectors, and yeah, so every particle has a different representation using these eigenvectors. So that's why phi I of A is different for every particle. And here you only optimize over A and B. Okay, so let's
Carlos,
yeah.
in the minimization problem, there is no regularization, right? So
No,
the regularization is only the choice of the number of eigenvectors that you keep.
Yeah.
Okay.
Yeah, because here, so you are imposing a lot of structure in, like you are optimizing over discrete curves. So you cannot, what you get is always very regular. It's not, there is no way that you overfit the data set using this discrete curve.
So in the number of parameters that you estimate, that A matrix, it's K by M minus 2?
Yes, yeah.
Okay.
It's cute.
Huge.
Well, it depends. So K is maybe, I took the order of 15 or something like this. It's not huge, no? I mean, if we compare with deep learning techniques, it's small, no? Okay, so yeah, let's look at the numerical results. Well, numerical experiment. So first of all, I consider this toy model where we have a two-dimensional structure. This is not anything biological. It's just a box with two arms. And the box can be deformed in either way. And the arms can move up and down. But I assume that this is my initialization, like my given atomic model. And then I generate a data set with a bunch of structures like this, yeah, moving the arms randomly and deforming the box. And this is a 2D structure. Then I compute this projection, and then I obtain for its structure a 1D density function, and then I add noise. I get something like this. So from this, you want to obtain this, and you know that so you know that all the structures are a deformation of this, and you want to estimate like how the arms move and how the box is deformed.
What's the sample rate? What's the box size
The box size.
when you discretize it?
Okay, so I have, so the length of the chain is 149. Then the distance between every 2 points is 4. And then the box.
And then when you make the projection and add noise, you discretize. How many?
How many pixels you mean?
Yeah.
I think it's written here. Yeah, I think it's 100 something. Yeah, 128. Yeah, is it good? Okay, I don't know if it's actually. Yeah. Okay, so using these eigenvectors of the graph Laplacian, we can actually visualize how this manifold of conformation looks like. So this is a projection of the three first eigenvectors. Yeah, and this is the 1, the 2nd, and the 4th, and so on. And then, okay, so in this case, of course, in a two-dimensional setting, we only need to estimate one rotation angle. So we want to estimate a function of this form, and we want to estimate this a hat. And applying RGD with this data set, this is what we obtain. So this is the initialization. It's the same for every structure. This is the ground truth, and this is the prediction. This looks more or less okay. It captures if the box is deformed or if the arms go up or down. Okay, but here we are not using any information about secondary structures. If we know that, in this case, we know that there is a box and then there are two arms. If we know that these box sizes and the arms are not going to be deformed, then we only have to, we can consider structures that preserve this secondary structure. Let's say the box size, box sides and the arm lengths. And then we only optimize over the angles that can actually vary. So the corners and the angles in the middle. So if we do this, then we obtain a almost perfect reconstruction. Yeah, so this is the initialization, this is ground truth, this is the reconstruction. But this is, of course, a very idealistic scenario where you know exactly what atom is being deformed. But the idea of preserving these straight lines is maybe something that can be somehow used in a real case scenario where you have these helices that will be transformed rigidly from one conformation to the other. And then for 3D structure, we have we have done this numerical experiment where we have this kind of molecular trajectory. And so we have 102 frames, but we have generated a data set with many of these frames from these 102 frames. And we have randomly rotated them and projected them to create this data set with, again, 4,000 noisy tomography projections. This is the representation using the eigenvectors. So in this case, it's one-dimensional because we have a protein, like a molecular trajectory. And here, in this case, we have solved this minimization problem to estimate these rotation angles. And this is what we obtained. So this is the initialization, which is the same for every particle. Of course, it's rotated depending on the particle. This is the ground truth, and this is the reconstruction. And okay, yeah, so to end my talk, so the conclusions is that we have a strategy to use this biological knowledge about how the protein should look like or how the macromolecule should look like, combined with the cryo-EM data set to estimate the deformation of these atomic structures. Then in our approach, so I think one of the advantages is that we can exploit knowledge about secondary structures, and this we know that in many cases a big part of the particle is not moving, so we can just estimate what we want. And then the numerical experiments in some toy models, in some toy examples, show that the method is likely to work in a more realistic case. But then, of course, there are things that we haven't addressed, like try to implement the method in a more realistic scenario, like if you have a big data set and you cannot compute everything so accurately. Also, the way we use the conformation, the way we use the pose estimate is a bit, we assume that we have a lot of information about the pose because we know we use the position of one part of the structure and we use the orientation of this part of the structure. And of course, this pose estimation may depend on the conformation. In our case, we are assuming that these parameters that determine the pose are independent of the conformation. But they are independent of the conformation, but they are not independent of the post-estimation. So this is something that we have to take into account. And let me finish this. And then we want to study also limitations of the method, because applying SGD over SO3, it can be problematic. But if we have not very big deformations, then it can be okay. But we need to study a bit more that. And then also apply this method to more complex structure when you don't have a chain, but you may have other ramifications. Yeah, that's everything. These are my collaborators. And if you have any questions, I'm happy.